First of all, I'll thank organizer for inviting me here. And coming to the topic, basically I'm from Directional Solidification Group of DMRL. Basically, we develop investment casting components for aero engine application, mostly nickel-based superalloys. This is the outline of the talk. Now, straightforward, these are some of the gas turbine engines, basically Western and Russian engines, and sheer the complexity and, if I may say, the beauty of this equipment shows that the best of the best minds, almost all the domains over the few generations have worked so that these devices are working the way they are. Inside, I mean, basically I have shown a cross-section of a typical gas turbine engine. It shows the pressure and temperature distribution. As expected, combustion chamber will face harshest environment, followed by the turbine section. Basically, that's what is my domain. And also, apart from the pressure temperature, the loading is very complex. In a sense, all sorts of loading. It's combination of fatigue, creep, thermomechanical fatigue, and also the fluctuating loading are experienced by these components. How to ensure that these components function their intended job is basically, of course, design is the first part. Second will be the selection of material. And since I'm talking about high temperature component, they have to be internally cooled, which I'll be showing subsequently. Apart from that, external coatings have also been developed. And yes, metallurgy, that microstructure part also becomes very challenging and crucial so that we can get these components function the way they are. Now from the turbine, this is the basically slide where I have shown a typical turbine blade. Because the turbine blade is a rotating part. Of course, as I said, the properties which are expected from these components, you can see, I mean, high temperature strength, toughness, creep, oxidation resistance, all possible things are demanded from this component. And that is the reason we are using first thing, material which are superalloys. These are internally cooled, of course, and externally the thermal coating kind of things are applied. And extra cooling, for internal cooling, it is not a straight basically. These are the serpentine cooling channels. They are not the straightforward what should I say, cooling channels. And also being an aerospace components, the dimensional requirement are also very strict. Now, the technology through which we can produce these complex internal and external features is basically what we call it investment casting. And investment casting technology per se, this is not a new technology. We have numerous examples, not only from India but across the globe, from Indus Valley civilization to Chola architecture, and across where this has been used to develop various artifacts. Even in our Sanskrit literature, basically, this particular lost wax technology has been mentioned. And if I may read the English translation, just as the copper melted by fire and poured into mold takes the very shape, so does the man take the shape of object comprehended. I mean, in India, basically, we have expertise in, or we can say that technology, science and spirituality has never been separate. So this is the best example of that. Even at present, our basically Dokra tribal communities, they are using the same technology to produce, some of the exotic, artifacts that you can see here. At DMR also, we are using the very same technology to develop the components, aero engine components. Some of the steps basically are listed here, starting from the die design, followed by clustering, shell making. I mean, this is the way our tribal brethren are making the statues which I have shown here. Now the material part, of course, nickel-based superalloy has its own advantages. That's the name suggests, superalloy, because they have better properties at higher temperatures. And the requirement which has been shown in the last slide, that results in a very complex recipe. I mean, I have shown here some of the elements starting from the aluminium to tungsten, titanium, rhenium, ruthenium. Very complex recipe is used so that we'll be able to get the desired mechanical properties. Microstructure also, these superalloys will have a panorama, married microstructure, having different phases, different what should I say, combination of phases, features. They need to be optimized so that we get the desired properties, so that the components which we are talking, the function their intended job. Very briefly on the evolution, of course, evolution has been on various fronts, from wrought alloys to cast alloy, from polycrystal to directionally solidified to at present state of our single crystal castings. Even in single crystal castings also, they are not solid, they are internally hollow. And also the internal hollowness I have shown, they are not straightforward. Basically, they are complex serpentine channels the way we are developing. The major research areas I have listed here, starting from the development of new alloys to better internal cooling system, because material has its own limitations. Now how to overcome the limitations, various technologies have been adopted. At DMRL also, we have developed some of the superalloys which I have listed here. They are the DMRL patented superalloys. Coming to the single crystal components, as I've said, the current state of art for aero engine gas turbine, basically it's a single crystal component. Single crystal, the reason are listed here. They have a better creep property, better thermal fatigue, and also corrosion resistance. Now the challenges in development of these single crystal castings are manifold. I mean, we are pouring liquid metal at something like 1500 plus degrees Celsius temperature, which is coming to the room temperature. We get almost all possible casting defects in any casting. Now coming to single crystal, we have additional challenges. We get, we call it sliver defect, and one of the most important one is the crystallographic orientation. The whole, in the process, basically, we ensure that by incorporation of these helical features, we are getting single crystal at the bottom of the casting, and which proliferate in the whole casting. But this is not just one crystal, it has to have a proper orientation also. That's the mention as 001 orientation. How to overcome these defects, how to ensure we are getting desired property, we have various options like cluster design, starter, shell system, and these are the technologies which need to be mastered, which need to understood. That's what we are doing at DMRL. Now I'll just briefly show some of the components which we have developed, and this is one of the first example, basically jet fuel starter. This is an auxiliary turbine engine. All our LCAs are flying with this. These castings we have developed, we have transferred the technology to HAL Koraput, and they are continuously producing this. Next one is for, these are the components for small turbofan engine for some strategic application. This also has, its own challenges, though it's a EQX, but the geometry itself, create a lot of issues, but we have, established this technology and in a process of TOT. For PTAE, these are the two casting which have been developed. For Aero engine also, this is the DS casting. Till now I have shown the EQX casting. These are a directionally solidified casting made from nickel superalloys only. And of course our Kaveri engine, because this is the program through which we have learned whatever we have produced till now. So all the blade vanes for high pressure turbine and low pressure turbine, these casting has been developed for various configuration has been supplied to our sister laboratories. And at present, recently we have established single crystal casting technology. And single crystal casting technology basically is not a straightforward, what should I say, all panacea for all the issues, because the problems comes from the shape also. Like the first example, this is the HTSC 1200 engine for helicopter engine. These are the, you can see there are smaller blades, solid blades. This we have developed in numbers, supplied to HAL. They are doing the further processing. Now as per the requirement, we are developing hollow blades also. But the major challenge comes in these casting. They are the larger component. They have a hollow feature, which are basically complex serpentine channel, vane, which has a double, cavity, and also the grain selector design has to be suitably adopted so that we get the 001 orientation in the desired fashion. This we have done. The numbers are produced, and near future basically we'll be supplying, and hopefully our sister labs will be using this. Of course, this is the last slide. Casting, whatever we develop, they are not used as such. There are lot of post casting operations, and till now we are relying on our basically foreign sources to get these things. This involves machining, brazing, and of course coating, which I have discussed in the first slide. DMRL in a process of establishing these post casting technologies also, so that we'll be able to develop not just the casting, but we call it ready to fit castings. Finally, I would like to acknowledge our director, Dr. R. Balamulikishnan, and other my colleagues and my, what should I say, superannuated colleagues who were for the last 40 years we have established this technology as DMRL, and hopefully we'll be able to achieve the global state of art. Thank you.